Good evening, everyone. And thank you, Dr. Balyan, for introducing about me. And I'd like to first thank the organizer for inviting me to this place. And then it's wonderful to see all the people. Yeah, so due to my director's absentia, please go to next slide. Yeah, I think, our institute belongs to a Department of Science and Technology. It's Autonomous Institute located in Hyderabad. And we also have two more extended campus. One is in Delhi, one is in Chennai. Can you please go to next slide? Go next. Next. Please, next slide. So far, many people have actually talked a lot about hydrogen, so I don't want to go into introduction details. So instead, I'll just go to the work actually. Can you please go to next slide? Next. Yeah, so coming to the hydrogen production. So far from morning, we have been hearing about 5 metric tons of hydrogen being produced by 2030, right? That's the whole target. But how are we going to achieve that $1 million question? As you can see, the cost associated, like we are expecting like almost 100 rupees to 150 rupees per kg of hydrogen by 2030. But that will be a real challenge at least in 2026. But we need to work on the particular areas. So some of the main areas what we are actually focusing on is how to reduce the cost of hydrogen production. So to address that, we actually started making our own electrolyzer instead of depending on the imported products. Can you please go to next slide? So this is where whole electrolyzer state of development state as of now. So for production of 1 kilogram of hydrogen, we need like 54 to 55 kilowatt hour from alkaline electrolyzer, and which is actually a highly matured technology. Whereas if we compare with the SOEC, which is like required only 38 to 40 kilowatt hour for production of 1 kg hydrogen, but still it is in R&D stage. Those there are a couple of companies started now installing this SOEC in India as well as in abroad, but still it has a long way to go. But in terms of a commercial system, alkaline is the topmost one, and second followed by with the PEM electrolyzer. Can you please go to next slide? So this is the one important thing on us to focus when you want to take hydrogen production for lower cost. So these are the main things. You need to have a lower cost, reduced cost volatility, better purity, improved safety, lower labor cost, and improved reliability of supply. So sometimes what we used to happen is we are an R&D institute, right? Sometimes we used to procure material from various countries. All of a sudden there will be some kind of ban used to come. So we have a supply chain issue. So though we have achieved some meaningful achievement in prototype, when I wanted to scale it up, we have a supply chain issue. So that has to be also addressed. So whatever you focus or whatever you are developing, make sure the material is available in India instead of going on imported ones. Please go to next one. And already Dr. Balyan has showed this slide, but I just want to highlight what is our focus is where alkaline electrolyzer, because the most of the component required for alkaline electrolyzer can be obtained or made it in India other than the membrane. Whereas if you look at PEM electrolyzer or SOEC or AEM, most of the components are imported or you need precious metals. So, and notably, if you look at the lifetime of the stack, which is much higher than any of the stack available in the other technologies, and more importantly for Indian ecosystem, this is much better because we already have a lot of other lagging issues. For example, if I take PEM electrolyzer, we have to have a high purity water, where water itself scarce for us of day-to-day life. How we are going to use for a electrolyzer? So that's one thing one has to focus. And moreover, PEM electrolyzer, the challenge in PEM electrolyzer is lifetime. So they are talking about a certain numbers, but meaningfully how long it works is again a question one has to ask. Whereas alkaline, since it's a mature technology, we may not have to worry a lot, but how to make alkaline electrolyzer is a challenge. Because in terms of PEM electrolyzer, the membrane is easily available, whereas in terms of alkaline electrolyzer, there is only one company which supplies a membrane, which is zircon based membrane. Of course, there are Chinese membranes are being sold. We have tried couple of membranes, but we could not able to have satisfactory result, whereas zircon has a challenge. So when we try to procure the membrane from membrane or diaphragm from zircon, they have a limitation. Initially, they have agreed on to supply several meters of membrane, but eventually they backed out saying they won't supply to Indian R&D labs at least. I don't know for industry, I don't know how it works. Probably the next speakers may talk about that one if they are having any opinion on that. But the zircon actually backed out. Then we need to identify a membrane for separating the hydrogen and oxygen which is being generated in the electrolysis system. Then we identified a supply chain. Now we are having no issue in continuing the work, and the membrane is as good as a zircon commercial membrane. Please go to next. So once we sorted out the membrane issue, we wanted to see what are the other problems associated in alkaline electrolyzer. The main focus, what we actually wanted to do is on electrode, because in alkaline electrolyzer, or most of the electrolyzer uses nickel or other kinds of precious metals. So if you look at the cost of nickel-based electrodes, nickel alone costs like almost 1,400 rupees per kg of nickel, plus addition of catalyst will further adds the cost for a electrolyzer development. But if you look at the non-precious metals, like let's say stainless steel, yes, it's an alternative, but it comes with a catch. So SS can be an alternative for nickel, but in the terms of alkaline electrolyzer, we are using a high concentration of basic solution, that is electrolyte, where we are using 5 molar KOH, which is highly corrosive in nature. So what happens is, when you are running the system in stainless steel in the corrosive medium, when high current, high voltage, it is running for like more than 1 year, what happens is it starts corroding. So that's a big question, one has to solve it if you are planning of utilizing stainless steel as an electrode for your electrolyzer building. Please go to the next one. So there then we developed our own coating technology, which I will be talking later. So these are the required components for making a stack alone. So your stack alone required anode and cathode, which is basically with nickel based electrodes. And of course electrolytes are basically nothing but KOH, which is dissolved in the water, or NaOH dissolved in water. Since water alone does not have a good conductivity, so to enhance the conductivity we add KOH or NaOH in the electrolyte system. And to separate the hydrogen and oxygen, which is done in your electrolyzer, we need to have a diaphragm or membrane, which is the commercial one which we are using, whereas the bipolar plate and all the other things are actually, we have obtained or we found a vendor or a supplier who could able to give us any time or any quantity how much we require. So whatever material required for our stack development other than membrane is completely made in or obtained in India. So this is just a stack alone. But whereas in terms of balance of plants, when they say electrolyzer, mostly people focus only on the stack, but that's not the only thing. So with the stack, we need to worry about the BOP as well. So most of the R&D institute or small industries which work on electrolyzer, they keep on talking about the development of stack. But the cost associated with electrolyzer is also comes from BOP. So that also one has to address if they want to bring down the cost of electrolyzer development, which we are also working on that. Please go. So these are some of the things which we are doing, and for in terms of making our own indigenous electrode, what we have done is we have taken the SS304 or 316 as an electrode, and then we developed our own wet chemical process, which we actually have a mild oxidation layer, which may have the nickel as well as other combination, which is acting as a durable layer, which acts as a protection against corrosive system. At the same time, because of composite layer what we formed there, it also acts as a catalyst. So which is having a beneficial effect of reducing cost as well as increasing the durability of the electrode. Please go to next slide. So once we established this one, what we found out is generally in R&D institute, what we do, we just develop a material and we publish a paper, we move on. Whereas in our institute policies mostly take R&D and take into a technology, so research into a technology. That's our basic mandate as well. So most times what we do, we start up some activity and we basically act as a bridge between academia and R&D between the industry. So most things we take it up to prototype and then we hand over to industry. That's how most of our activities we do. And then as we basically done the electrochemical studies and we found that the material is good, as well as the chronopotentiometry also identified as given as an idea, the material is highly durable in alkaline medium. Can you please go to next slide? I do not go to scientific stuff over there. And then of course we tested the stability of the electrode in 5-hour testing, and we identified the electrode developed by our methodology is highly durable. And once we established that, then we wanted to make a BOP components as well. Can you go to next slide, please? So in the case of once we establish stack, the challenge here is when a hydrogen and oxygen is generated from an electrolyzer, it does not come only as a gaseous medium. Instead, it comes gas with a liquid. So you need to separate the gas and liquid. So we have developed a gas liquid separator. Basically, this is a gravity based separator. What happens is liquid will be collected in the bottom and gases will be collected on top of the one. Of course, we established a dryer and other component required for this one. Please go to next slide. So once we established that one, we have went on to develop, this is our prototype which was developed. And when we started running this prototype, we found out it is working, But we had a challenge. As you can see, the end plates are started bending. So it could not able to withstand high pressure. Of course, this was initial periods which we are not aware much. Then with lots of iterations, we could able to solve the problem as well. Can you go to next slide? Yeah, this is just a small videograph just to showing our prototype which was developed like like 8 months back. And of course, we have tested its hydrogen production and oxygen production capability, and we tested the purity of hydrogen as well, which is like more than 99.9% hydrogen and then more than 99% of oxygen as well. Please skip the video. So yeah, once we established, then we went on to modify the stack by using a metallic end plates or FRP placed end plate, and we identified that could able to withstand the pressure as well. But with the time, what we understood is there is lots of resistive issues as well as the stack size is a big challenge again for us. Go to next slide, please. And once we established the stack, we wanted to validate in identified a BOP company where they are manufacturing a BOP, and then we validated our stack there, and we identified our stack is as good as a commercial stack available in the market. Go to next slide. So then we understood how the commercial stacks are available in the market. So initially when the alkaline electrolyzer was established, there was most of the alkaline electrolyzers were made by using narrow gap cell. If you can look at the schematic diagram or the photograph of the stack which was actually developed in our lab like 8 months back, like the same 1.5 kilovolt stack is like almost 185 mm, whereas with our further fine tuning of material as well as the removal of material and then stack design modification, we reduced the size more than 100 mm. So the whole dimension of a stack size is decreased, and this is more compact and more cost effective as well. And in terms of hydrogen production as well as in terms of current required also, we found that this is better. Please go to next slide. This is how our whole evaluation of our perovskite, our electrolyzer work has started. We started with a small stack from 100 watt. Now we are ending up with 1.5 kilowatt with a hydrogen production of more than 0.2 nm cube with a power requirement of 50 to 52 kilowatt hour per 1 kg of hydrogen. Of course, this is still evolving process for us. So what we identified is, once we establish this one, our focus is only establishing a prototype. But what happens is when the industry came into contact with us, so their requirement was different. So what they told us is, we need a stack, but not just at 1.5 kilowatt. We wanted up to 10 kilowatt. Because our R&D activities are like, or most of the R&D institute, what they do it in a small level and they leave it. Whereas when industry comes to the contact or they are trying to join hands with us, they actually support us in terms of financially as well as taking the technology. Then we go for a larger scale. So with their confidence and support, now we went on for 3 kilowatt and now 5 kilowatt is under production. Please go to next slide. And then this is one of the small prototype which was established recently. It's a complete system with all the required component. This is a 1 kilowatt system which was established. And even the recent Iran war is actually helping us, because one of the industry recently contacted us, how about utilizing the same electrolyzer for producing hydrogen gas, where they have a hydrogen stove with them, so they wanted to join hands with us, where it can be a portable hydrogen stove, where it can just use it as a hydrogen supply unit, instead of depending on the LPG gas, and then they have their own hydrogen stove which can be used for their day-to-day application instead of depending on the LPG issue if some future it comes. Yeah, this is again the planned one. That's it. Can go to next slide. And this is the recent one which we actually, this is the last one, sir. So other than the traditional alkaline electrolyzer or PEM electrolyzer, we also established ECM, that is electrochemical methanol reformer. This is other technology where instead of using traditional water or KOH, where methanol can be used as a electrolyte and which can be used for production of hydrogen. So as you can see, this production of 1 kilogram of hydrogen required 70 kilowatt hour, which is very economical. And successfully this technology was transferred a couple of months back, and MOU was signed in November only in Bharat Mandapam, and last month the technology was also transferred to an industry called InfoEra. Please go to next slide. And now this is under production. Yeah, next slide. Yeah, that's it. I'd like to thank our institute heads and then of course my group members who are part of this work.
Thank you very much.